Katarzyna. We are both from Poland, from Astronomical Observatory from the Jagiellonian University in Krakow. And both of us will be dealing with cosmic rays driven dynamo. And today we would like to shortly introduce the cosmic rays driven dynamo. First, why cosmic rays? Let's answer this question. Then I introduce some basic process with cosmic rays and magnetic fields. Then I show the MHD equations, which are very well known here. And then we show some applications of this model to different types of galaxies. First in local approximation, and then in global simulations. So, cosmic rays. Why we have to dealing with them? Because when I was learning about interstellar medium, in the books we can find out that in ISM consists of three major components. This is magnetic field, thermal gas, and cosmic rays. And from observations we know that gas, magnetic fields, and cosmic rays are in equipartition. So dynamically they can be important in the whole evolution. We can ask a question where they come from, cosmic rays. Yeah. So in each explosion of supernova in interstellar medium, each explosion releases energy about 10 to the 51 ergs. This energy, about from 10 to 30%, is converted to acceleration of cosmic rays, especially for electrons, protons, and heavy ions. So when we know where they come from, we can also ask how do they evolve. Yes, they have very each single particle from cosmic rays has very high energy, and the speed of each particle is about the speed of light. But when we take a group of particles, this group evolves in diffusion way, because in interstellar medium or in universe we have much turbulence. The turbulence causes scattering of cosmic rays particles each other, yes, and also on magnetic fields. That's why we have diffuse propagation. And the diffuse propagation, it's not the diffusion, it's anisotropic, yes, because of that cosmic rays are charged particles. They feel magnetic fields, especially electrons. And we have to, when we would like to describe the evolution of cosmic rays, we have to assume that they diffuse anisotropic with respect to the local magnetic field. And we divide the diffusion tensor into two components, parallel and perpendicular to the magnetic field. And the ratio of perpendicular component to the parallel is about 5%. When we would like to implement these cosmic rays to MHD simulations, we have to use some approximation. One of them is done by Schliekeiser and Lersch in 1985. They proposed that we can use diffusion advection equation to describe the evolution of energy of cosmic rays energy. The fluid of it's a kind of fluid in the code. So fluid is described by the adiabatic equation of state, and in this equation we also add a source term, which is the source of the cosmic rays in the interstellar medium. I come back to this term later. And the diffusion tensor, for example, which is described by Ryu et al. In 2003, it has this expression. And here we can see that this is this is computed with respect to the local magnetic field in each particle, in each cell. Okay, so when we have cosmic rays and the thermal gas in the stellar medium, the main problem with cosmic rays is that they are weightless. They don't feel gravity. So when we assume that we have stratified medium like in a galactic disk, and in that medium we have cosmic rays, they, because of explosion, they would like to escape in every direction. And one of these directions could be vertical to the disk midplane. So the cosmic rays are going upwards, but and they drag with them gas and magnetic fields. But the gravity is I draw it in the board. We have a galactic midplane. Here we have some thermal gas, and the gravity force is that way. When we inject cosmic rays here, they would like to expand in every direction. They drive the magnetic fields, but the gas feels gravity. The cosmic rays are weightless, but gas feels gravity. So the gas is falling down along the magnetic field lines. But this part is becoming more lighter. So it goes more it goes up. So this system is unstable in that sense. And also we can see that this system can be that this instability can be in some sense self-sustained, because when we assume we have two explosions of supernova, and this is here's one of them, here's the second. We have the evolution of cosmic rays, but the gas is falling down, and here we have a dense region. And once again, after here the stars can be formed, and after a while here starts the supernova. The explosion of supernova occurs, and so on and so on.
Do you use that to determine the position of new supernova explosions?
No, not yet. In the simulations we use random, some random procedure which finds the place where we explode the supernova, and that's all. Okay, when we are in the galactic disk, these magnetic loops are twisted because of Coriolis force. And to work this system in the sense of dynamo, we have to assume also a dissipative process to convert small space magnetic fields, which are produced by such explosions, into large scale magnetic fields. This conversion is done by magnetic diffusivity and reconnection process.
But to the problem, generally you don't need diffusion, right? Because anyway, this
but
all the loops,
reconnection needs diffusion.
right? If there will be very small loops, the average will be net zero. They don't need to merge physically into one loop. Right? Generally, you don't need it.
Yeah, but we need reconnection.
Summer diffusion, yes. Magnetic diffusion, you mean?
Yes.
Say again? Yes. Yes.
Yes. And we cannot
No,
compare.
but for different reasons, not because the small loops don't merge.
No. What when
You need to lose some flux through the surface. For this you need diffusion, but not to merge the loops. The loops can continue being small scale, everything
but
will
we
work.
would like to reproduce the observations where we see this large scale magnetic fields.
How you distinguish two loops like that or joint one is the same thing.
We don't see large scales, we see averages.
But this is not the case when we have one supernova explosion. When we have turbulent motions, the magnetic fields can be twisted around, and the average could be zero.
No, it won't. If there is Coriolis force and if there is an alpha effect, it will not.
Maybe that question we should readdress at the end of the talk, maybe when Kando is also back up online again. So let's continue in the meantime.
Okay, and now I would like to switch to numeric stuff. This is the set of MHD equations which we are using in our codes. The thing that I would like to mention here is following. Here we have a gravity which is included into the equation of motion. This term is only used in the local approximation, which was today nicely introduced by Olivier. But the most important thing is it's a gradient of cosmic ray pressure. This gradient of cosmic ray pressure cause that that we have some coupling between cosmic rays and the thermal gas. Let's draw a picture. Here we have gas. Here we have cosmic rays, and assume that gas is uniform. But in the cosmic ray distribution, we have a 2D Gauss distribution of cosmic rays. And when we start to evolve that system, because of that term, the gas would be pushed out from the center of this gas. It's because it's only because of that term. So when we would like to explode a supernova in our code, we just put some 3D Gauss in 3D distribution, Gaussian distribution of cosmic rays, and then it evolves like an explosion of supernova when we have shock. Okay. And in our simulations we use adiabatic equation of state, also in cosmic rays and also in gas.
So, excuse me, could you go back?
Yes.
So the evolution equation for the energy of cosmic rays, but you already have shown, is included in the system.
Yes, it's included.
It's not shown here, but it's included.
Yes, they are included. Yes.
And maybe you excuse my ignorance, but why do the cosmic rays don't feel gravity? You said it several times. Because these are particles, so why don't
yes,
they?
but they have
Very low density, yeah.
yes, low density and high energy. Each particle has
Okay, this is an approximation, so
yes,
But
but
neutrinos.
yeah.
I mean, here neutrinos are included because also they don't interact with materials.
See, the cosmic rays will feel gravity, but the only thing is that the number density is so small.
Yes.
But they are coupled to the gas because waves
Interact.
they produce due to the streaming instability, which is what is the cause of this pressure which we are talking about. This couples them to the gas
Yes.
all the time.
Is it possible that the cosmic rays are trapped in the magnetic bubble that we created? Or are they energies?
In magnetic lobe.
The magnetic bubble we're creating, we have a gradient in the magnetic field, and like an Earth ring current, we have a population of trapped particles. Can they be trapped there, or because you just on the board is sketched that they just go down there, but I don't know.
No, they not go. This what's going down is gas, not cosmic rays. Cosmic rays is going in any direction. They only the gravity is the matter in our code. Matter is the matter feels gravity, yes, but the cosmic rays they can do everything that they want. Mostly, they have to evolve according to these equations, where we have only diffusion with respect to the local density.
Also, I think you wrote the cosmic ray equation. If there is no perpendicular diffusion, then they cannot cross the field line.
Yes.
But because there is a perpendicular diffusion in the cosmic ray equation, in principle they can cross at a very slow rate the field line.
Yes, that's right. They are not trapped in the, but they okay. For example, this is one of the tests of cosmic rays in code, in our code. We have the same situation like before, but we have here magnetic field. Okay? And the evolution of this 2D graph after some time would be like this. And also, because of that, thermal gas, also evolves in different way. They also produce something like that, but here we have another feature.
But generally, in the random time-varying magnetic fields, magnetic bottles are either short-lived or improbable. But otherwise, these are judged particles. If you create a magnetic bottle, they will be confined to it. Up to the diffusion.
again, they will be confused.
Of course, yes. There are charged particles. Like any other charged particles, if you create a magnetic bottle, they will be kept there.
But you can escape the bottle if they are perpendicular diffusion.
Yes. They will escape because of this, which is relatively weak.
Yes, 5% of the
Okay. Now I would like to switch to the applications of cosmic ray driven dynamo. First, simulations were done in case spiral galaxies. What was included that we used same profile like Olivier today's mentioned in his talk, described by the Katia Ferrier. The supernova explosions are the local sources of the cosmic rays. We assume 10% of the energy of supernova, and this was done for spiral galaxies, and I was dealing with regular galaxies, and they have very feature, but I think I should move further. Okay, this is one of the plot for my simulations regarding irregular galaxies in local approximations. Here we can see the normalized total magnetic energy and normalized azimuthal flux for these simulations, and as we can see that this dynamo works quite well, and after mostly 1.5 gigayear we have a saturation of this dynamo, and also the large-scale magnetic fields, which we associate with the B5 flux, is also growing, and when we calculate this in units of microgauss, these numbers are mostly equal to 1 to 5 microgauss. So this is the field which we really observe in the network.
When you say local approximation, you are solving only Z or something?
Excuse me?
What do you mean by local?
Local approximation, that was described today by Olivier. We assume we have a galactic disk, and we just count some blocks. And we here introduce the centrifugal force, Coriolis force, and we are only simulating that region. And also we see gravity.
Then you also have shear, right?
Yes, shear, of course.
Alpha
Yes.
omega then.
Yes, yes.
And can you get an alpha squared dynamo if you go to rotation?
I don't remember that. I'm not sure. Okay, I would like to show what's happening in the curve. On the left hand side we see the density of the gas, and the right hand side the energy of cosmic rays. Okay, let's stop for a while. This is the time when the supernova does not explode. Yes, this is only just simple evolution, and we to reproduce some bursts of activity, we just switch off for a while the supernova explosions. So when we plot the supernova explosions rate during the time, we get something like that, which can be associated with spiral arms or or burst of activity in some region of galaxy. And let's wait for another explosion. This is not good. Once again, maybe. I think it's hard to see, but we cannot see these arrows. If they would like better result, then this will look like this. Yes, the loops, Parker loops, are can be seen here. So,
what's in the center? I mean, they look inverted, so that's
okay.
That looks inverted version of this.
Just one wavelength. One wavelength.
When you have low density, there's higher cosmic ray.
Yes. Yes. Here we have on these vectors are velocity, and here are magnetic fields. And in that point explodes a supernova. Yes. And because of this pressure term in the fluid motion, it pushes the gas out. Yes. And because the supernova explodes here, we have a large number of cosmic rays. Okay, and what's the thing with irregular galaxies? That with them is there's a let's say big problem with them, because they are very slow rotators. They have low shear rate and low mass. The irregularity mostly comes from the explosions of bursts of activity in some region. Well, for example, when we have slowly rotating disk, which is regular, and for example, in that place explodes lots of supernova because of the burst of the activity and the concentration of gas. This destroys the rotation curve, because, for example, the typical velocity, rotation velocity for irregular galaxies is about 40 kilometers per second, but one explosion of supernova is more than 50 kilometers per second, and this destroys that's why the rotation curve is destroyed. But nevertheless, the magnetic fields which are observed in irregular galaxies have same values like in typical spirals. So it's quite positive. And the results are following that cosmic rays driven dynamo seems to be working in irregular galaxies, but more study is needed. That's my current project. In the results, I also find that 20 to 30% from the of the magnetic fields which are inside the disk are ejected into the halo. This ejection is caused because of weak gravity in the irregular galaxies. So the explosion of supernova accelerate the gas and also the magnetic fields, and they can be easily ejected from the disk. This was predicted by Kronberg and Bertone et al. That dwarfs can seed in intracluster medium. Okay, I think that's
So, why does it work? You said it seems to work. The rotation, the irregular, the shear is low.
yes, the shear is low and the rotation is long.
So then, how did it become supercritical in terms of the dynamo number?
Actually, I don't know, but the simulations.
So that the mean field builds up.
Yes.
If the shear is really low, then you still infer that it is an alpha omega dynamo,
Yes.
although the shear is low.
Yes.
So, but nevertheless, one could expect that it is at least maybe an alpha squared omega dynamo, where the second spot where the alpha acts is no longer negligible because of low shear. Isn't that true?
Yeah, maybe, but I didn't check it.
So Hubert just described the cosmic ray driven dynamo model and some simulations in the Schelling-Vogel approximations. And now I'd like to show you some global simulations of galaxies and of cosmic ray driven dynamic galaxies which we are currently making in Krakow. However, before that I will show you the first simulations, the first global simulation of cosmic ray driven dynamo made by Hanash. And they use the same model of cosmic ray driven dynamo which has been described by Hubert. However, they assume that no magnetic field is represented in the initial configuration. To build up the galactic, this model they use the relative Milky Way gravitational potential and the gas distributions as well as supernova array and its spatial distributions is based on interstellar medium model proposed by Perrier. And to do the simulation they use the Pierre-Lix code. Okay, so here you can see how the toroidal magnetic field components evolution in time. So at first you can see that magnetic field is completely random, and this is because it originates from randomly oriented supernova explosions. However, later on you can see that magnetic toroidal component of magnetic field forms spiral structures with well visible reversals in the disk plane, and this magnetic field gradually evolves to larger and larger scales, and here you can see that toroidal component of the magnetic field has the same direction in the disk, and the volume occupied by the toroidal magnetic field expands gradually to the end of the simulations. Okay. Okay, so here you can see how the magnetic flux and total magnetic energy growth looks like, and you can see that from the beginning of the simulation we have exponential growth of the magnetic flux, also the total magnetic energy. However, here you can see that the magnetic flux change its sign and its absolute value varies randomly around this exponential curve, and this situation corresponds to the magnetic field structures, the magnetic field evolution. Okay. What is more, magnetic field separates at time equal for gigayears, and the growth of the magnetic, growth time of the total magnetic energy is close to the galactic rotation period, this equals something like 300 megayears. And these simulations strongly support the idea that the galactic dynamos may have been initiated by small-scale magnetic field of stellar origin, and that's why we decided to use this dynamo in our simulations, which we are currently making in Krakow. So currently in Krakow we are working on, for example, on magnetic fields in barren galaxies, and here you can see one of the most spectacular barren galaxies. This observation was made by Bell And here you can see the polarization map. The contours, contours are the polarized intensity, vectors are the magnetic field vectors. And the main observed feature of this galaxy can be summarized as follows. So the polarized emissions from ridges coincided with the dust lines along the edges of the galaxy. Magnetic fields change quickly their pitch angles when they are located upstream to the dust lines, and this results in the polarization valley to the telescope beam, as can be seen, for example, here and here. And the most important magnetic arms are visible in the other part of the galaxy in the inter-arm region. So we decided to reproduce the magnetic configuration of this galaxy, but
Katarzyna, it's in fact, unfortunately, it's not that clear. For example, in this galaxy, in this specific case, we were looking very carefully at this, the southern arm.
yeah.
For example, their magnetic field is large in the arm, so the picture is mixed. It's not that clear.
Yeah, but
That's
this is a good example of. There are not so many observations of magnetic fields in Barrett galaxy, so this is the best example which we found.
Yeah. Indeed.
Excuse me. For the galaxy can be non-educated, could you explain again what we see on the picture?
Oh, okay. So, okay, starting from the last one, so here you can. Oh, but what we see.
Oh, it's just the symbol. I see arrows, I see
Oh,
islands,
okay.
and I see colors.
Okay, so contours are the polarized intensity. Okay, arrows are the magnetic field vectors, and here you can see just gas distribution. Okay, and
So the gray is the distribution, the magnetic field intensity.
no, it's gas distribution. The gray.
Ah,
Okay.
I think it's optics, right? Optical photograph.
Yeah. It's not magnetic field. Okay. So before we start to simulate magnetic field evolution in global galaxy, you have to construct the hydrodynamic model of this galaxy. So our Barrett galaxy is composed of 4 components. So first, rotating disk of star, massive halo and bulge, and the non-symmetric potential of the bar is described by second order Ferrous ellipsoid. We introduce the bar gradually in time, and here you can see the bar semi-axis. And this is the rotation, the available velocity of the bar of this non-symmetrical potential. And the most important part now is that at first we didn't include any dynamo action in our simulation. We just start with some magnetic field and check how it will evolve during the simulations. And in our simulation we use the Godunov code, the code which was written by our friend from Krakow, Grzegorz Kowal, who now is in Brazil, yes. So here you can see some of our results. So here again we have the polarization maps. So again contours are the polarized intensity, vectors are the magnetic field vectors, and they are superimposed onto the Hall intensity. And so in the beginning our galaxy is in the magnetohydrodynamic equilibrium, so we have just plain this. However, after almost 1.5 rotation period, you can see that in the central part we have the highest density, and also the highest values of the density are visible in the other part of the galaxy. And all these Gazelle structures are constructed due to the non-axis symmetrical potential of the bar. And this non-axis symmetrical potential of the bar also influences of this initial azimuthal configuration of the magnetic field. So we can see that at first magnetic field just follows the gas distribution and is aligned along the Gazelle's arms. However, as the simulation proceeds, you can see that magnetic fields detach from the Gazelle's arms and drift into the inter-arm region. And here you can see well visible magnetic arms in the inter-arm region. And we believe that this drift of magnetic arms into the inter-arm region is caused by by the fact that the pattern of the gaseous arms rotates faster than the disk itself, especially beyond the rotation radius, and that's why the gaseous arms move further in this, while the magnetic arms stays in the inter-arm region. Okay?
Can I didn't understand what you say. Firstly, is the field axisymmetric?
Yes.
Okay, then secondly, why is it concentrated in those spiral arms?
Because here,
Yeah, even in the beginning.
because there is a high intensity.
High,
So here we also have some magnetic field, but it's not so high value like in the arm.
yeah, so why is it more in the arm? Is it
Because
supernova more or
No. There's not no magnetic. Any dynamo is included here, no supernova explosion. So this is only because there is the highest density, and this density caused that magnetic field.
So it just got compressed.
Yeah, exactly.
But then it should get wound up very tight eventually. Is that what's happening, or is it just frozen in? Or it's not frozen in?
No, to be honest, after 1 giga-year we don't see any magnetic arms in the inter-arm region, so they are only visible in.
So is there a dynamo going on here?
No. In this simulation,
just
yes,
frozen
just
in?
to check how.
Okay.
This is just the redistribution of the magnetic field.
Right. But then it will decay eventually.
Yeah, exactly. So that's why we decided to add to our simulation dynamo action. However, as you can see, we can reproduce some aspects of those observations. And so a few months ago, we decided to add to the Godunov code the cosmic ray transport, and to can make simulation of cosmic ray driven dynamo in our galaxies. And
Sorry, is there a differential rotation created consistently?
sorry,
The differential rotation, was it plugged in, or was it created by the turbulence and the rotation consistently?
no, the rotation is
Is rigid,
yes. So, but of course, there is none of this.
but the turbulence could have created a differential rotation, and I would expect that.
Yeah, but there are no supernova explosions.
No, no,
Okay, so let's see. So we have decided to add the cosmic ray driven dynamo to our model of the galaxy. So we start also without any magnetic field in the initial configuration, but we simulate our galaxy from 1 giga-year, and after that we add supernova explosions, which also add magnetic field into our computational domain. And of course, supernova explosions distribution depends on the gas distribution, so the highest number of these explosions is in this gaseous arms. And here you can see some of our preliminary results, so we are currently working on it. However, here you can also see some magnetic arms in the inter-arm region. However, the growth of the energy is not so fast as we wanted to it be, but we are going to make many different simulations of cosmic ray driven dynamo and waiting for our results. But I will show you also another type of the galaxy which we are currently simulating, and this is the galaxy which was described by Oliver during his morning talk. And I will only say that this galaxy is excellent. This is excellent test for the cosmic ray driven dynamo model, because here you can see that magnetic field cross inner ring without changing the direction, and this is and magnetic field just form coherent spiral pattern. And this is to opposite what is usually observed in so-called grand design spiral galaxies, where magnetic field typically follows the gas distribution. So we have decided to also to simulate this galaxy. And however, at first summarize, we have to, of course, reproduce its hydrodynamic structure. So here you can see that this part of the galaxy is only in its inner part, so this is the inner ring, which can be visible here. But this galaxy has also spiral arms and faint outer ring. And as we know, the ring formations occurs when gas is driven by the gravitational torque of the rotating stellar bar. And the bar is now presented by oval disk, and in this case we have both small inner bar and also the oval disk. So to reproduce this model of the galaxy, we have to use two non-symmetric potentials, so inner small bar and oval disk, and we have to use the angular velocity of these two non-symmetrical potential in that way to locate the inner ring by resonance and other inner resonance exactly where the rings are observed. And currently we have made some hydrodynamic simulations, and we obtained this inner dense ring as well as the other fine disk. Okay. However, I cannot show you any simulation of the cosmic ray driven dynamic in this galaxy because they are currently running on our cluster in Poland. Okay? And to summarize, so cosmic rays are definitely not very important, and local simulations of these shearing box simulations confirm that it works good and can amplify magnetic fields to offset values. What is more, it appears that it also works good in spiral and wide galaxies. What will happen in Moon galaxy, we still don't know. This is the test of cosmic ray driven dynamics. And to finish, I want to invite all of you to attend in the conference in Krakow, which will be organized in Krakow, in Poland. And the conference will be about magnetic fields, of course. And here you can find the website of our conference. However, I think that it doesn't work now because we have some problems with servers. But you can just jump in your. Okay, so.
Thank you.
The experimentalists will suddenly be excluded from that conference.
Kilometers.
Not
Could be meters.
Change
it to meters.
You can make it meter and then include it.
However, we found it after the title of the conference, was,
Oh, it's the parts that ones that easy.
yes, but
when you see magnetic field with supernovae, right? Then you put what, a quadrupole, a dipole, what do you put for the
it doesn't matter to be honest.
But then when it gets sheared, if it's changing, then it will get destroyed also.
But is it global simulations? So in my global simulations, one supernova explosion is just one single circuit. So it doesn't matter if it's bipolar, quadrupolar, or is it just a point.
So you don't have a resolution. But then, no. How do you get such fantastically ordered spiral patterns with this supernova seeding? Is what I want to understand.
To be honest, these results I obtained, I don't know, 5 days ago. They are just first.
No, because you put some, let's say, a dipole or a quadrupole or something, and then you shear this, right?
Yeah.
You get changing signs, which will get sheared out into all kinds of stuff, and then I don't know what exactly happens. But if you have lots of supernovae which are seeded, then you get a mean, which is maybe amplified and the fluctuation may get destroyed. But if you are just a few supernovae, then...
I think in simulation there are lots of supernovae. Yes,
this simulations, there's a lot of
supernovae. There's a lot of supernovae.
Yes, and they eject random... They eject random magnetic fields in the disk. So because of the magnetic diffusion and the
Yes,
shear,
yes,
they are converted to the order.
There was some claim at the meeting at the school here so far that cosmic ray dynamos would not be fast dynamos. Somebody mentioned that.
No, it's fast dynamo. It's,
Yeah, but somebody else in the school said no.
Yeah, I think that was me.
you said that we have problem with diffusivity, yes, that we cannot use small values of the diffusivity. So currently we are using 10 to... this value of so
And the growth rate depends on the value of the diffusivity?
to be honest, I don't know, because as I said, I have only one, in the sharing box approximation depends, yes, but I don't know how it will be like
So
in
In
global
sharing
simulation.
box, there's the problem that when we have, I don't really, when we have high diffusivity, the ratio between the radial and phi component becomes different. When we have the some number of the diffusivity equals 100 in the units of parsec and megahertz, then the ratio becomes 1. Yes. The ratio between BR and B phi component into this. But when we change the value, the ratio is different. So in that sense, this system is dependent on the magnetic diffusivity. But in the global simulations, Michał Hanasz used smaller value of diffusivity.
But there you also inject magnetic dipoles, right? Do you
Yes.
have, do you have global simulations where you don't include dipoles, but just
No.
the cosmic ray energy?
No.
And can you
But
get
when you don't inject dipoles,
Yes,
you
there's
have
no
to
problem.
you have to introduce the seed filter into this.
Yes.
But in the global simulations, there were the seed fields were equal 0, and only the stars inject the initial magnetic field.
But I know that it doesn't matter if you start with some seed field or if you add it during supernova explosions. The glow rate it's almost the same.
So in order not to be too late for our drinks, not to be too short for that, let's continue. The next talk will be by Stefano, and he will be talking about kinetic simulations of plasmas.
Right. I will be fast. This work has been done in collaboration with Giovanni Lopenco at Catholic University in Madrid. Just a brief outline. I will start giving an introduction of the problem. I will give you a motivation of our work, and I will introduce the numerical equation and the numerical scheme we're going to be using. The main part will be about the implicit particle insult, which is the numerical technique that we are using for solving kinetic equations, and their development and implementation. And I will end up talking about the results. This talk will be about mostly numerics, so there will be no such a deep physical content. I will talk about mostly about kinetic simulation of collision and plasma. As we've seen today, collision and plasma are a very common plasma in the universe, in particular for plasma, for instance, for dynamo theory are present in hot accretion dips, in a galaxy cluster, and in interstellar gas. We didn't talk about too much, but the plasma dynamos in fusion experiments, such as the reverse fringe device, are collision as well. So far we saw all MHD simulation. You might ask yourself when MHD are not enough. MHD breaks on the scale, on the space scale, where the electrons and ions follow different dynamics. Typically, these scales are, depending on your problem, under your consideration, are ion general radius, ion scale depth, or several at divine height. Just for give you an example, So these scales are very, very small if compared to the global dimension of the system. So luckily for people who are doing MHD, kinetic effects are very important on very small scale. As example, kinetic effects are important in current shifts in the diffusion region of magnetic reconnection. In the front of collision and shocks, that means that the shock thickness is way less than the mean free path for the particles. At the interface of and finally interface of plasma with different properties, such as plasma with different temperature and density. Another characteristic, kinetic code typically are very good in describing interaction between wave and particles, and describing especially the exchange of energy between wave and particles. In particular, MHD is not able to describe resonant effect between a wave and particles, because for MHD you have only, for each point you have just the velocity that is the average velocity, and you don't have the whole description about the velocity distribution. So you won't be able to have describe the resonance effect that depends on the particular velocity of the particle population. If you talk about instabilities, wave particle instabilities and their effect for dynamo theory, you will see that people did consider wave instabilities in connection to dynamo, and particularly they consider wider instabilities that occurring in the front of the shock as a possible creation of magnetic field, and in particular they look at gamma ray burst and just from active nuclei and cluster of galaxy. There is a very recent paper about is an EPJ 2010 talking about band instabilities that could enable magnetic field via cosmic rays in proximity of the shock front, and what is considered the opposite of instability, the damping of the wave given by the interaction of particle and the wave, is actually important on small scale magnetic fluctuations. So as you can see, we weren't able to describe the dynamo on very large scale because those are not still reachable by our scheme, but we can work on many topics very strongly related to dynamo. Our goal is to study numerically the coupling between the microscales where the kinetic effects are very important, and the macroscales where the system usually evolves. Unfortunately, if you try to solve simply the Lagrangian equation, you will see that the numerical constructs are too much severe. You really have to solve very small scale and have very in order to have numerical instability. To solve this problem, the fact is to have very small time step and grid spacing, we use implicit numerical scheme to avoid this problem. Kinetic simulation can be used in context of dynamo theory. I just to give an example, mostly about magnetic reconnection. That is our main topic. We work on a small scale kinetic instability as well in anisotropic of plasma, and we work on a plasma producing in labs. And we are trying to study small scale turbulence. The governing equations, we have the main equation we are trying to solve is the Glasgow equation, also known as Jeans equation or Boltzmann collision equations. Is a conservation law for the distribution function Fx. Fx is the probability of finding a particle in the position in the phase space point xv around the volume dx. So the distribution function is described by the evolution of the distribution function is described by the Vlasov equation. The evolution of the magnetic field is described by the set of the Maxwell equations. And these two, Vlasov and Maxwell equation, are in relation by the moment equation that makes the problem nonlinear. There are many different numerical techniques, as you probably know, to solve this system. You can do find a difference in the phase space, so it's going to be a six-dimensional space. You can use Fourier Hermite transform method, and they all have their own advantages and disadvantages. We use the particle in cell method. That is the most used method to solve the kinetic equation, probably because of its simplicity. The method itself is based on two basic ideas. Instead of solving directly the Vlasov equation, we represent the distribution function by a reduced number of computational particles. The initial distribution is a sample, and the Vlasov equation is solved by calculating the equation of motion of the particle. So in the particle in cell code, we won't solve the Vlasov equation itself, but instead, for each particle, we will solve the Newton equation of motion. The second basic idea about particle in cell is the introduction of the grid. At each time step, the charge density and current density are just calculated by interpolation. For each cell, we count the number of particles, we know the charge of that particle and the volume of the cell, and we are able to calculate charge density. Knowing the velocity for each particle, we will be able to calculate the current itself. Once we have charge density, current density for each node, we will be able to solve the Maxwell equations on the grid. Okay, so we just solving the Maxwell equation on the grid, we reduce our problem. So for each time step, the basic peak algorithm is composed by 4 stages. As you see before, you have integration of particles. We solve for each particle, we solve that for the that is the equation of motion. We do interpolation to the grid to calculate charge and current density. We solve the Maxwell equation on the grid, and then once we know the electric field and magnetic field, we can calculate the electric field and magnetic field acting on the particles, going back to the particle by interpolation. Depending where is the particle, we can actually calculate what is the electromagnetic field acting on the particle. As I told you before, this is very simple and nice. There are two major problems that are given by the numerical scheme. So it's not physics, it's just numerics. The time step must at least 1/4 of the plasma period. Plasma period is the basic oscillation in the plasma. If it displays electrons, they will start oscillating, right? So the time step is very, very severe scheme. That means that during this oscillation, you must, the time step has to be at least 1/4 of this oscillation. There is not one.
Well, you have implicit code, right?
Yeah, this is. I'm talking about why we want to have implicit scheme.
Mm-hmm.
So this does the basic algorithm. I'm sure why we need to go to implicit scheme.
Mm-hmm.
The grid spacing must be less than the divide length. This is typically the shortest space scale in the system, and this is to avoid a numerical instability called green instability. As you said before, one idea is actually to go and use an implicit scheme. You probably know that from your class of numerics that if you're able to solve the implicit scheme, you will be able to reach anti-initial instability. Looking from the perspective of what it really means, implicit particle itself. So you have a set of dA for each particles, and you have to solve for the position and velocity of each particle. This position and velocity of the particle will depend from the electric field, the magnetic field, the future time step. In the same way, the electromagnetic field will depend from the velocity and the position at the future time step. The solution in implicit particle in cell require the solution of a huge nonlinear system where each line is composed. If you think about the matrix that you need to solve for your full implicit peak, each line is composed by equation of motion for particles plus the Maxwell equation at each grid point. Okay, so instead of having those 4 stages, in principle, the implicit scheme is just requiring the solution of one big non-linear system. So for a long time, this has been impossible to do, and not solvable. And even if it was, the time required to solve such a system certainly will not be convenient from the computational point of view. At the beginning, at the 80s, there was a major effort, mostly coming from Livermore lab and Lozano's lab, in numerics community to solve the implicit peak problem. The solution was to actually decouple the equation of motion and the Maxwell equation, introduce additional equations. The additional equations are, in this case, are Taylor expansion of the charge density, recurrent density. Okay, so you have Maxwell equation, you need the charge density, recurrent density at future time level. But you don't have. You use the previous charge and current density, you make a Taylor expansion, and you substitute in the scheme. So in the Maxwell equation, you will have additional terms, and that will contribute to the scheme. Once the electromagnetic field are calculated using the contribution of the charge density, current density, the future time level, you can actually you find electromagnetic field and a magnetic field at the future time level. I can actually move the particles, each one. You might ask yourself, is this advantageous? Implicit particle cells are stable typically on ion scales, and because of the big difference between ions and electrons, the typical separation on the time scale and space scale is the square root of 1856. So implicit scheme works on the scale of ions, and the simple scheme that I showed you at the beginning works on the electron scale. So you will have, using the implicit scheme again of in time step.
So you move both of them, that means many times it is very difficult to probably solve the motion of both the ions and the electrons.
Yes, we both. So we are not reduced schemes. You probably are mentioning there are some hybrid code where they have electrons are fluid and the ions are particles. This is because you don't want to solve. But in this case, you basically remove the plasma frequencies from the system.
The point is you move only the electrons. Okay, very good.
So in some cases, like kinetic instabilities, what people do, because kinetic instabilities are occurs on the scale of electron scale.
Yeah.
Electron scale, you can imagine the ions as motionless, very massive, let it there.
Yeah.
But still, you need to neutralize the system.
Right.
So you did add some contribution from the ions, but you let it there. You don't let it move. But this actually can be done only if you have kinetic instabilities. What they are called micro instabilities. That depends on the.
Now, of course, one would like to move everything, but I thought that there was some computational problem of trying to follow both these guys at the same time. But you are obviously solving.
No. Well, in many cases, if you are doing. Yeah. So you need more computer power, more memory, but and actually the results they will be the same. It mostly depends on the work that you're doing. It would be actually stupid to do some electrostatic instability using implicit scheme, okay? Because it's less computation intensive, and you need just to say on electron scale, right? Because you are interested in the electron scale, like Weibull instabilities or string instabilities are typical there. Yeah. So depending on what you want to study, you choose the scheme. Of course, this scheme is very good when you're working on the ion scales. Kubernetes connection.
This code is something which you have developed, or?
Yeah, we have developed this. I will talk about it. So as you can see, the gain you can actually reach is very high. You can actually have a speed up to 3 million times in a 3D simulation. There are disadvantages. One big disadvantage: the code will be uglier. Okay, it's much more complicated. That means that we require much more development time. People usually, when they develop code, they don't think about that, but it's actually it takes much more time, and there are many more code bugs in the code, even though you are a very good programmer. And typically, because of this, it requires more the evaluation of the charge and density at the future time level. It typically involves calculation that are 5 times than the typical scheme, basically a scheme. I think Chris mentioned that in MHD, implicit schemes are not so efficient because they require much more computation. In this case, you have 3 million times gain and 5 times less in comparison to the basic scheme. So it is important to use the implicit scheme. We developed the scheme. We had Cartesian geometry. We have a version that is 2D and half and 3D. Yeah, for solving the Maxwell equation, we use finite difference technique, box scheme. We develop our solver and mostly generalized linear residual and conjugate gradient solvers. And to solve the ODE of the particle, we use predictor correctors. The code is in C++. It's called IFIC, and we use a very strong object-oriented design. And we actually were very careful in order to use auto-vectorization of the compiler. So we basically check, especially on the particle part, that the computation intensive part were rightly vectorized, and where they were not, we actually changed the code in a way that we can use SCC instructions. The code is a parallel. We use a general domain decomposition technique. So we basically decompose the grid we divided the grid among processor depending on their position, and we divide the particles as well. Whenever a particle is exiting from one domain and entering the domain, we just communicate on the other processor. We use MPI library and mostly obviously blocking communication, even though we do planning to go to asynchronous communication. We use OpenMPI, but we in the particle mover, but we didn't see any real performance improve. I have to say that probably this is due to the fact that we didn't really work on the algorithm part, but we just use OpenMP in the current state of our data structure and in our formulation of algorithm. Probably if you arrange the algorithm itself, we will be able to not incur in performance decreasing. Yeah, we do think so. OpenMP, we think that this can probably due to the fact that whenever you use an OpenMP, we have some compiler optimization that didn't work. And the other big reason we observe cache competing from different threads. So this is something that we're going to work on. We need quite large runs. We mostly run on Pleiades, that is a NASA supercomputer, and this big2 in Leuven. And because I use in Illinois, we did run up to 10,000 processor for magnetic connection problems, and everything was fine. Just to show you some how powerful it can be in an implicit scheme. I just show you an example of the connection. At the beginning, you have a current sheet. You have so you have magnetic field going in one direction, the other direction, and the interface you have is a region where the magnetic field is zero. And to support this configuration, you have, in this case, a current, electron current going out of the plane. You like to hold the system, and the topology of magnetic field is rearranged. Exactly the same kind of simulation took 3 days on 64 processor using implicit scheme, and it took 4 days and 10,000 processor on Roadrunner, that is the fastest supercomputer in the world.
So was there an instability or something which led to this current sheet breaking up?
Yes, it's a clear instability. Yeah, yeah.
Do the results agree, or to what did you benchmark this against?
So they didn't agree, and we thought that the reason why they didn't agree is because they were using electron-positron plasma, and we are using not realistic. We use as mass ratio of our simulation 64. So in plasma physics, whenever you can actually change the mass ratio between electrons and ions to compress the time scales, right? Mm-hmm. Okay, so you artificially change the mass ratio of electrons and the protons, and you basically make the phenomena that the occur over the plasma frequency. You already know cyclotron frequency. You make them happen faster. Okay, in principle. No, that's what happened. So we think that they couldn't afford to go up to 64 because of their scheme, their numerical scheme. We did actually more than that, just using 64 processor. So we didn't see any stability they saw, and we thought that because we have different mass ratio. So, but we're going to do exactly the same simulations. So 10,000 processor for 4 days is a huge simulation. It's probably the biggest simulation at least in the particle simulations.
I mean, if these are comparable physical simulations, then that's either too good to be true or a huge waste of computing time in the past.
No, it's actually not true. So the implicit scheme doesn't resolve the electron scales. That's where is the problem. So we are not running with their definition. They really need to solve the Debye length. We don't. Mm-hmm. Okay, because we are using an implicit scheme. However, we don't resolve those scales. So we need some people to verify our results. Okay, so that's one major step of the implicit scheme. So until people want to see that the two simulations agree, there will be some people saying that the implicit scheme doesn't resolve the electron scales where the physics is, so it cannot be taken seriously. So we still need their simulation, and of course they're very happy too. This is a huge number of processors. So they were actually very happy to see at the conference that we were showing exactly pretty much the same simulations, using 64 instead of 10,000. On the need to do 10,000 processor simulation, there is probably a need because, as I told you, we are not resolving the electron scales. We are more working on ion scales. That's why we are.
But if you went down to the electron scale, but with the implicit scheme, you could still have a gain because the time step is larger.
Yes.
This would be maybe the honest comparison then.
Yes. So we did that. we did that,
And what's then?
and the results are very good.
No, I mean in times, in computer time.
Oh, so
You have the same
we
resolution,
did
but
a simulation that was on 10,000 processor with electron scaling, and it was 4 hours.
Oh, that's interesting.
Yeah. So it was actually very good.
It's still a huge difference.
We did simulation on magnetic connection in reverse field pinch, where dynamo effects, of course, and we did simulation as well on instabilities. Even those kinetic instabilities, they occur on electron scale, so you really need to use your implicit scheme with very small time step in order to resolve these instabilities. So
What is this?
also, this is the phase space.
Are those two-stream instabilities?
Yeah, so this is two-stream instabilities. We wrote a paper comparing classical relativistic dynamics to show the instability. I used this code for doing that. So this is just to show you that why people may want to use kinetic scheme in dynamo theory. If they really want to look at this stream instability as possible mechanism to make magnetic field, they have to go to the kinetic code. In conclusion, I'm talking about this implicit particle itself. The code is runs on parallel machine. We have done quite large simulation, and hopefully in the future we'll be able to apply our kinetic code to simulate phenomena related to dynamos.
Thank you.
Question, please. Yes, yeah. You said you truncated the Maxwell's equations in Taylor-Rich-Mountain to the second order. Do you know how much you're losing there? Do you know how accurate?
Yeah, so for instance, for my PhD thesis, I did even the full implicit scheme. So I took that huge, I took that very large nonlinear system and I solved it. And comparing the results, there was no difference. And I would say that the point is with the Maxwell equation that you really don't need the distribution function, because you just need the charge density and current density, that they are, just an integral information. So to answer your question, I would say I didn't notice any difference. But of course, this probably depends on the particular system under consideration, right? So people actually develop different implicit scheme, just using different evaluation of the charge and current density. They say you're in a situation where you have a strong magnetic field and you can apply the drift kinetic equations, right? So you know the drifts. And you can actually calculate a priori the trajectory of particles and estimate, give an estimate the charge and current density. You can go higher order at your Taylor expansion, but from what I did, I didn't see better energy conservation. That's what people look in this case.
When would you expect it to break down? If you're at a high Mach number, or would you use not?
Also, when we expect the implicit scheme to break down because of another numerical instability. It's called grid instability. That's the only case. Of course. So whenever you do implicit scheme are very powerful method, but they do have some caveats. Okay? So the best thing is to understand your physical problem and to choose the right time scale where you want to work on. Okay? So if you're interested in some particular instabilities and use too much large time step, the implicit scheme is going to be very dispersive. So it's going to change the nature because of the nature of your problem. Just going to change the dispersion relation of your of the plasma. So you have to be very smart and understand the physics first, and then go to the scheme and decide where you want to put your salt, the time step and grid spacing. Okay, so because otherwise you're going to lose something because of the numerics. Okay.
Yes, please.
Do you have any simulation on firehose instabilities?
Yes, I have here too. Viable instability, like
not viable, firehose. Like,
yes, yeah, we have a paper on firehose instability.
Those kind of things that I can do with nobody.
Can we get a question?
No, I was just wondering that since you are interested in doing something to do with the dynamo, there are two aspects which are interesting. One is, firstly, since you can resolve the ion scales at least, there are these questions which Alex Shekoshin and Amar mentioned, reading about the plasma instability and their role. But that has to do with the viscosity. If you want to do anything with the resistivity, then you probably have to resolve the electron scales. Because most likely the resistivity will get affected by phase particle interactions on the electron divergences.
So,
rather than the ion divergence.
but in this case, resistivity, because there are no collisions.
Right. I'm talking
It's
about
only anomalous resistivity,
anomalous.
and it's given by your instabilities. If your instability is about on the ion scale, you can actually work on the ion scale. What I'm worried about, you have instability working on the electron time scale, and you're using too large time scales, you're going to lose it. It's going to the numerical scheme is going to just damp it. So, for instance, people estimate the anomalous resistivity given by low Rehabi instability. That occurs on very large scales. So you can actually, depending on instability that you want to check, you can actually pose yourself in that range of study. You don't have to follow the electron scale. Because it's anomalous resistivity. It's not real condition.
Yes. But don't you need some resonant transfer of energy, and then, or you are happy with this wandering of? Because I mean the electrons are having some gyro radius, and all.
So we are not making average on the cyclotron frequency. We are doing average on the plasma frequency. So it's basically the motion. If you displace electrons from neutrality, this is gonna just oscillate. In the normal scheme, you really need to solve this scheme. So if you use a time step that is too large, the electric field is just giving the result.
Yeah, we'll talk more.
So, we have now a talk by Julian Mack, and he will be giving an introduction to shallow water MHD.
Well, speaking of Van Gogh, I have here a picture by Escher. See if that works. That works.
Is that in the simulation?
I wish it was. I wish I could claim ownership of that. Let's see, Control L. Okay, hello. My name's Julian, and I've just started at the University of Leeds as a PhD student, and I'm being supervised by Professor Ted Hughes. And today I'm going to give you an introduction to the so-called MHD shallow water theory, which was formulated by Peter Gilman in 2001, or maybe 2000. Minor details. The essence of the talk is I'm not really going to be talking about the dynamo theory as such. I mean, potentially the shallow water equations could, no one's really investigated it too much, but potentially it could support a dynamo theory, mainly in the sun. This is where the initial motivation came from. But I'm not going to talk about this because that's not really what relates to my research. I'm just going to talk about the mathematical abstract properties of these equations.
So where did these come from in the first place? Okay, actually, I need to draw a picture of it. Just as a caution, I don't have any pictures on this thing, or I don't have any graphs either. I have lots of equations, but try and finish on time. Okay, so you have the sun. Give it quite big, isn't it? Well, that's the core in here. Apparently, it's a bit like a Scotch egg. I'm not quite sure about it. Okay, this is not to scale, so let's call this the radiative zone. Right. That's not right. Convection zone, radiative zone, and a core. And where the takt line is, it's sort of situated around here. Well, on the layer bordering the convection zone and the radiative zone. That here. And as you might, it's very thin, it's about 7%, 0.7%, so radius. One of the interesting things about it is it's stably stratified, it's very stable, it's been detected by heliososmology and it seems to persist for a long time. One of the things people have done when they sort of discovered it was they ran it in a simulation and they suggested, well, let's just put it like this. Put it in a purely hydrodynamic model. And what they found was that it didn't persist. It just gets destroyed because all the momentum gets transported to the pole. So this shouldn't really exist in a hydrodynamic model. So it's obviously a magnetic thing. It's believed to be quite important in the solar triangle because it's a layer under strong shear, which is because the core and the radiative zone is approximately rotating at uniform speed as a solid body. But then, as we know, the convection zone rotates as it's got differential rotation depending on the latitude. So here it's rotating faster, but here it's rotating smaller. So as you go up the latitude, you have a difference in the shearing of the this particular area. So one of the things that I've actually studied is the dynamics of the dynamics and instabilities of the takt line, specifically using this model. We'll see what happens in a few years, so we can actually get anything useful out of it. Okay, what are the shallow water equations? So the initial motivation of doing this is most people have modelled the takt line as a spherical shell, so you have something like this. You have an R dependence, but then you just fix the R dependence and say, well, nothing depends on R. Essentially, there's no radio structure. But then, this restricts it quite a lot. So what the shallow water equation, the motivation was, see if we can relax this restriction ever so slightly to include some vertical structure in things. But it's also very nice because the shallow water equation was initially developed in the geophysical fluid dynamics model, in modelling the atmosphere and the ocean. And these have been very well studied for the past 100 years. So potentially we could bring a lot of tools and results derived in GFD and see if we can generalise it to MHD. And I'll explain this slightly further. Mathematically speaking, as a mathematician, I find the shallow water equations more interesting in terms of its mathematical properties. I mean, it's I've listed some of these ones. It's hyperbolic in structure, which is different to the full MHD equation, because if you put diffusion in the full MHD equation, it becomes an elliptic equation, which is you've got a different structure again. One thing you could do is, because of the hyperbolic structure, you can write it as a Hamiltonian formulation. And from this formulation, one of the really nice things is all the conservation laws drop out really easily. Numerically speaking, there's some, because of the symmetries that exist in these set of equations, you can, well, some of the numerical schemes have exploited the symmetry into, so to sort of make it slightly more efficient, and some of these schemes are interesting in themselves. But one of the other things is instability and Salisbury coins, which I have slightly leavened about that, but I might just skip it over. Okay, as a quick derivation, what I'm going to do, I'm going to derive the GFD shallow water equation quickly. The SWMHD equations just fall out. It's just the same, more or less the same assumption. So I have no, so just to make clear, I have no diffusion. I have no topography, so the bottom layer, there's no first variation, I just have a flat bottom. And I assume I don't have rotation either, and I assume the pressure is continuous over this free layer I have, so I have a free layer. So I'm going to draw a picture. It's obviously slightly easier to understand. Let's have a look. So what I have is, for example, something like this. Rigid bottom. This is a layer of fluid. I would denote the mean depth by h, and the deviation from the mean depth, for example, this, by little h. Okay, I'll just leave it like this. What I assume is that the horizontal length scale, L's right here, is very big compared to h. So this approximation, essentially, I'm not actually going to do any maths with it, I'm just going to say what happens with it. When you do this thing, you would, because the horizontal height is very small, the vertical velocity becomes less important than the horizontal velocity. And from this, one of the implications of that is the vertical velocity is balanced by hydrostatic pressure. Because of this, you can also, because you also have an assumption that pressure is continuous over the layer, you can integrate out the Z dependence completely. So I still have, essentially I have a 2D structure. H here, you still have a Z structure, but it's described by H here, which is completely described by X and Y. So you only have two explicit dependent variables. To do it slightly more rigorously, you could do it in an asymptotic series and expand by small aspect ratio. But what happens with the equations that come out in the GFD case are these. So phi here, I use phi because I don't use u, because I use phi here because phi I denote by the horizontal velocity u phi 0. These are essentially 2D structures. And because of, the mass conservation gets modified accordingly, because of the free surface, and this is just a consequence of the equation. And this is the simplest case. You could put lots of things back in. So you can put back diffusion, you can put back rotation, you can do it in spherical geometry. You could even do something called the multi-layer model. So instead of just having one layer, you can stack up several layers. I think this is what next slide is about. Depending on what model you use, you end up with the gravity term being slightly different across the layer. Each layer is, if you have a multi-layer model, each layer is governed by its own independent set of equations. But it's the reduced gravity and H term which changes over the layers. One way I would see this is as a finite difference, sort of approximation to the whole continuous case, potentially. I mean, one thing someone spoke to me about yesterday was that I was speaking about this, and he was saying, well, if you can solve the full MHD equation, why the hell would you bother doing this anyway? It just looks extra complicated. Well, it's a potential model, so you can't sort of throw it in the bin before you've investigated it to see what happens. One thing I need to probably say with this is that if you just have a single layer, which for the moment I have, you don't have any sort of vertical structure with it. So you can't do convection, you can't do temperature gradients, So basically you can't do any of the interesting things you want in the tactical line, but it does do shear. So one of the thing I'm doing is shear, an analysis of shear flows on these equations. And as is well known classically, there are lots of wave solutions you can construct just from these. Okay. So what happens with the SWMHD case when you put a magnetic field through? Well, it's influenced by a magnetic field. It's just the same derivation, essentially. But instead, you would use you would write the J cross B term as for example, a B dot graph B term. Put the magnetic pressure into the potential. So you now have a magnetohydrostatic balance. Because you've got the J cross B term, you put the magnetic tension in the momentum equation. To complete the description of the magnetic field, you need the induction equation. And just to close it up, you would use conservation of magnetic flux. And with this assumption, unfortunately, one of the things you would have to do is you have to assume this interface is actually a magnetic line. But again, these can be potentially relaxed. From that, the conservation of flux is actually equation 7. And I've recently seen a paper by someone, Cordella, I think, who has investigated in relaxing this condition a bit to see what the effects are, and I've yet to read it completely, so I can't tell you anything about it at the moment. But these are the set of equations derived by Peter Gilman in 2000, I think. I think it's 2000. And these are set of equations. Again, the momentum equation I've said you would get roughly B dot graph B term. I've probably sucked in 1/4 rho factor into it, so B has the units of velocity. That's Fiber's induction equation. I just prefer writing it that way rather than graphical whatever. It's just the same thing. Okay. Any questions so far about how this is remotely applicable to the sun? It's just the abstract set of equations.
I'm thinking applications to galaxies could maybe also be.
Yeah, I'll speak about it in a bit. I recently read a paper which some mentions about that. Well, with the sun anyway, one of the models, because you have a free surface, you would possibly use the approximation to the overshoot layer of the tactile. So it's sort of in the one that straddles the convection zone. Or even that it has been shown that if you use it as the underlayer, straddling the radiative zone, it's not as good because for the obvious reasons. And but then one of the things I will be investigating eventually is the multi-layer model, where you could have, for example, with rigid boundaries, you don't have to have a rigid boundary. What if I have another deep motionless layer bottom? That would be called a 1.5 shallow water equation, like a multi-layer. So I could have really random things like 7.5 models and see what.
Excuse me. What's the reason for no viscosity or diffusion?
At the moment, it just makes it easier for the mathematically speaking.
Probably good.
It's just easier. You can look at it. It's in the books. I mean, there's no point in doing.
You don't expect anything more from it.
No, I'm just throwing out just for the derivation.
Okay.
Just because the extra terms just make it complicated when you do a derivation. Just because I'm late. Okay. So from an abstract point of view, what do these have? These have waves, again, like classical things. But all of these are modified by the magnetic effects. And these are one of the things you need to emphasize, that these are essentially different to the ones you have in the classical case. For example, with the Rossby wave, which is one of the large-scale waves you have on the Earth, where you can observe on the Earth, and to a less extent on the ocean, the magnetic field actually splits it into two modes. So you have one which goes slightly faster, so a fast Rossby wave, and a slow Rossby wave, which you can do the same. For this one, the slow wave limit is sort of really close to the hydrodynamic Rossby wave. you would expect. Gravity waves, again, exist. What gravity waves are, for example, if you have a bathtub, you just drop the water on it. Because of this, vibrator carries out a wave vibration. I think that's the one. I can't actually remember. And various waves exist, and these are papers. And going back to your point about galaxy, I recently read in, I think it was Henning Stokowski, about 2009, they are working at the Institute of Advanced Studies at Princeton. So what he did was, in his paper, on his keyword, he put, analysis of shallow water waves. Keyword, neutron star, black holes, X-ray burst. Wrote some stuff about it, and just proceeded with complete mathematical analysis. Conclusion, there's nothing, in the conclusion, nothing is mentioned about neutron stars, X-ray bursts. So you just sometimes think, do they just put these keywords in just to show, or are they actually trying to be clever? Okay. Again, you would expect the SWMHD equations to behave like the classical ones. You would expect the same conservation laws, etc. So energy momentum stuff conserved. Magnetic flux is conserved. Magnetic helicity, I think, is conserved. I haven't done anything to the induction equation, so it should be fine. I haven't checked it. Actually, one of the things is most of these haven't been checked.
But you need 3D, right?
Yeah, that's what I would have thought. But
3D?
Oh no.
Essentially, these models are essentially 2D. Actually, I think the flow is okay, because the flow is essentially 2D, but the magnetic field is still a 3D structure. I don't know. One of the things I'm slightly more interested in are something called the Casimir invariance. Actually, I'm not going to talk about it too much. What I'm going to talk about in the remaining 5 minutes is something called potential vorticity, which is slightly less well known. Well, it's very well known in the GFD case, but not for other people. It's just one of those really obscure things. What's nice about PV? Well, you remember you have magnetic helicity appearing as a pseudoscalar. So a magnetic helicity is something like for example, appears under integral. It's not very useful that way, unfortunately. It's a bit ungainly. PV, I think it's F, which is the planetary vorticity, plus the relative vorticity. What's nice about this is that this is a function. This is materially conserved, just as a function. So it doesn't appear under integral or anything. So it's actually really nice in this way. And this is physical, but I can't remember what the explanation for it being physical is. In the classical GFD case, what people have been doing with PV is that because it's one of the conserved quantities and it doesn't appear as an integral sign. One thing people have done is to use it analytically, improving, for example, stability variant, looking at the dynamics of flows subject to PV. I think one of the things about PV is that it does actually give you the dynamics if you convert it accordingly. And also in numerical codes, because you can use a materially conserved quantity as a tracer. And there are various methods on studying the dynamics of, for example, the atmosphere using PV. For this one, I'm going to go on to that in a bit. But again with PV, there's some stuff you can use in semi-Lagrangian methods, in Lagrangian numerical methods, etc., etc. Again, when people have checked it, when Peter Gilman derived it, I think one of the things he hoped was that PV would be conserved by the SWMHD equation. It doesn't. It doesn't come as a quantity. It doesn't come as a quantity outside of the interval. However, from the hyperbolic and Hamiltonian formulation, what people have found is that actually Casimir invariant Q, arbitrary function of Q, something like this, that's conserved. But again, it appears under integral, which is slightly unfortunate, but maybe we can do something about that eventually. Casimir invariants are basically things like, it comes from the structure of the equations themselves rather than as any physical thing. Well, there are two things which are possibly physical. The circulation is the integral of vorticity, and entropy is the integral of vorticity squared. And one thing I should emphasize is that these are only for ideal MHD, ideal SWMHD. If you put diffusion back in, all of these get destroyed. And, well, I want to get drinks, so we'll skip this. Okay, as a conclusion, what I've done so far is I've introduced a potential model for, approximation to the full MHD equation as a potential model to studying some of the problems that exist in MHD. For example, the dynamo problem, in the sun, the transport problem of how things, how matter gets and momentum, etc., gets transported around the sun. What I've glossed out is some of the more mathematical things like hyperbolic structure, other things. Applications, I haven't talked about them at all. I probably should eventually, but give me the 2 years. I'll probably do some more other stuff. Numerical methods I haven't even talked about. I mean, some of the ones we expect the methods to use for SWMH, for classical shallow water, to have an analog in the MHD case, but again, this has yet to be investigated. Again, this is because this is a dynamo workshop. If you want to look at the dynamo-related papers, there are many papers by Ducati, and just look on the website. There's a whole set of them. And yeah, 6 o'clock, bang on.
Thank you.
Sorry. No, they investigate the instability problems in the dynamo code, which potentially has use in dynamo.
But that doesn't have any magnetic fields. It is purely hydrodynamic.
At the moment, so I mean, they are looking at these potential models. Whether they get anything out of it, or whether I get anything out of it, it remains to be seen. Okay.
Thank you, first of all. An inspiring talk. Questions, please. Yes.
Did you say the magnetic field in the shallow water MHD equations could have vertical structure? It was a little bit confusing.
Yeah, that one I need to rethink. Actually, can't think at the moment on the spot because it's 6 o'clock and dinner time. I don't know. I'll get back to you on that. I mean, from the applications I've been using, no. But I need to go and sit down and actually do it.
There will be some physical process which will be controlled by the shorter time scales across the layer. But some will not. So you have to just reasonably choose the range of problems to solve, and you will be absolutely.
Yeah, I think that's one of the things I would actually criticise myself is, as a mathematician, I'm not all that concerned about it. I like the, one of what I like is that I like the, investigating things from an abstract point of view, potentially relating to physical problems. But I agree with, the PhD I'm having to do. I need to be a bit careful on what I use and apply it to.
In the pure shallow water thing without an HD, you can work out a whole theory of statistical equilibrium. Yeah. So that the structure is depending on what conditions you start and to maximize entropy function. Okay? Is that expected as well when you put the magnetic field?
No, I'm not sure because one of the one of the things is that it's because this is quite a new theory. I mean, from counting, I can count about 20 papers which have been done in the past 10 years, rather than compared to something like 500 papers done on the shallow water over the past 100 years, for example. That I'm not quite sure about, so I can't answer the question.
it all relies on the existence of all these invariants.
Okay.
The entropy, so how they press the Casimirs.
Yeah,
It still will be.
they do. Yeah, they do. I mean, the Casimirs have actually been. I mean, those ones have actually been proven to exist. So whether you can actually derive something from that, no one's done it. Someone could write it.
May I just make a comment? There was even an experiment, experimentally, this application of these shallow water equations to galactic disks motivated an experiment with rotating shallow water where to study the spiral patterns. There was an analogy between the stellar dynamics equations and shallow water equations identified in the 80s, which led to an experiment with the spiral structure of galaxies with shallow water layers.
Yeah, well, it's one of those things. I sort of looked through it, and then looked through the literature on it, and then why was it only written in 2001 or 2000? I can never remember which one it is. Why were these equations only written then and not any time at least 20 years before when people have been looking at MHD stuff? Weird. Just one of those things that seem to have escaped the people.
Yeah, right. There was no type line back then.
Yeah, that's true.
But the C was there.
Came into some of the later.
The US pattern.
Okay. There's one other application to this, that's giant planet atmospheres.
Yeah.
The group of James Jones.
For example, I think one of the ones that Chris Jones occasionally does is the surface of Jupiter, which has potential. I don't know if he uses shallow water. McIntyre does a lot on shallow water.
It's related that a lot of the close-in hot Jupiters are tidally locked, so they always show the same. And they are interested in heat transport in the atmosphere, whether the planet can get the heat to the dark side or not, and whether the flows are suppressed by magnetic fields and so on.
Yeah, well, McIntyre loves the potential photos. He has written loads of papers. And one of the things he did suggest about potential photicity is really good. And unfortunately, it gets, because you know how helicity sort of, it gets destroyed, but not dramatically. PV on its own gets destroyed with an arbitrarily small magnetic field. Numerical investigations have been looking at that, which is unfortunate. But that's probably one of the price you pay for having extra structure in it.
Any other questions?
Yeah. How would you put the magnetic boundary conditions in the upper surface, which is a free surface?
Yeah, that's a good question. And again, I need to get back to you on that. I need to get back to you on that. I'm not really there.
Yeah, I mean, he's probably thinking of a potential field boundary condition that you can't probably.
Yeah. Again, it sort of depends on whether this B has a what kind of vertical structure it has.
In the original formulation, it was a pressure equals 0 boundary.
Yeah.
So thinking about real shallow water.
Okay. All right. I suggest that we continue talking over beer and wine, and so in that respect, let's go down to the third floor, in front of 32. So, thanks again.